All right, so I'm presenting today on enough statistics so that Zed won't yell at you. Okay? My name is Devlin Daly. So I contacted Zed about this talk and I asked him, if I'm going to present this, is it really going to be enough so that you won't yell at somebody? And he said, no, probably not. But you can try. So we're going to try it today. Let's see what we can do. Okay? Some caveats. I am not a statistician at all. Okay? I'm actually into digital identity, so if you guys want to talk about OpenID, OAuth, SRP, simple permissions, anything later on, I'm the guy to talk to about that. But I've taken a few classes on statistics, and Pat wrote me into this, and it's all Pat's fault. Okay, so some of the things I'm trying to do today with the presentation is to familiarize some of you with some of the vocabulary with statistics and just some of the basic concepts. Okay, so the basic concept of why statistics came about is because of models. Okay, so models should be pretty familiar to us because software itself is a model. Okay, so there's different models of how the planets orbit the sun, in elliptical orbits. Now, they're mathematical models, so they're not actually real life. That doesn't mean that they're not useful. And sometimes they can be very useful. Okay? So statistics came about is because they would have these equations describing the motion of the planets, but the data didn't actually fit the model perfectly. There was always this error function. And it was always off a little bit. So the statistics is actually the study of that error of a model. Okay? So for instance, if I ask you, what is the temperature of the human body? Okay, so this isn't actually just one number because that temperature is going to vary. Okay, so we say, well, it's about 98.6 degrees Fahrenheit, but we'll see, well, it's distributed. So this is the standard normal distribution that we're all used to, the bell curve. So the things that we can learn from this, can you see my pointer? Good. Is that the 98.6 would be right here at the average. Right? So that's the center of this distribution, and then if we measured it, then it's going to be a little bit more, a little bit less all the time, a little bit of randomness all the time. But with the normal distribution, then we can tell with the area underneath the curve how much of the data is how close to the mean. So these are standard deviations, so within one standard deviation of the mean minus and one plus, we expect about 68% of the data will fall within that range. And if we extend that to 2 standard deviations, then we'll expect to see 95% of all the data within that range. So that doesn't mean that all data is going to be there, but on average, we'll see about 95% of it. Okay? So this is the normal distribution, but when we go to measure something, it's not always a perfect normal distribution, but it is a distribution. And so distributions are characterized by where the middle is, which is usually the average or a mean or some metric of middle, and then how spread out they are. And that's the standard deviation is the spread. Okay? So to kind of explain a little bit more the play between the two is, here's 2 different samples. We got the blue and the orange. And these 2 distributions have the exact same average, except one varies quite a bit more, is that there's a lot more spread in the data values in the orange. So for instance, if this was a web server, then we say, if we were just looking at the averages, then we say, well, the performance is the same because they have the exact same average, but with one, since it's varying greatly, then we know that something is seriously wrong with our web server and we need to investigate it. Okay? So coming back to finding the temperature for the human body, is that in order to find the true average temperature, so now we're talking average, so there's not a single temperature, it's a distribution. And to find that true distribution or the true average, we would actually have to measure everyone in the world. Okay? So that's what we call population. So if we're going to do of all the human race, or if we were looking for the average for everyone in this room, we would have to test everyone in the room and get their measurement. Okay? So if we're looking about the world, then this is something that's not even possible. Or even what's the average weight of an elephant? There's no way you could actually weigh all the elephants in the world. Okay? So what you have to do is you can't actually measure the population directly or exhaustively, so you have to sample it. And all a sample is that we take a subset of the population and then we use that to estimate the main population. Okay, so the population is the thing that we actually want to measure, and the sample is what we can feasibly measure. Okay? But this sample needs to be representative of the population, or we're going to get completely bogus data. So, for instance, if we're looking at the average height of people, and the sample was my family, then I'm short for my family. I'm 6'2", and so we would conclude that everyone in the world is around 6'6". Okay, so that's totally bogus. So we need to make sure that our sample is representative if we're going to try and infer it back onto a population. Okay, so I'm going to get into a little bit of statistics of comparison, but before we get into that, we just need to know that the sampling is a key part of statistics, and that we need to have good samples, and that is how we manufacture good data. That's the only way that we know what actually is truly going on. Okay, so one run of any benchmark or any test is not a distribution, that's a single data point. Okay, we need to have multiple samples so that we can see the variance in the samples and to be able to identify the distribution. All right, I work for Phil Windley. I think a lot of you may know him by reputation. One thing you might not know about him is that he loves Diet Coke. He runs a conference and he makes sure that there's always 5 times as much Diet Coke as any other beverage because he loves Diet Coke and he's not going to run out. Okay, eat for breakfast every day. So let's say that we have Diet Coke and we want to know, can he really tell the difference between Diet Coke and Coca-Cola Zero? Can he tell the difference, okay? So we need to, how can we design this experiment to actually find that out? Okay, so if we think about it, like, well, we could give him one of each. So if we let him taste a cup, we're not going to have it labeled, of course, then he's going to pick either Diet Coke or the other. And then the second one, well, it has to be the opposite. So he has a 50-50 shot of just guessing that right. So that's not very good. So if we give him just 2 cups, then we don't know if he's just guessing or if he actually can tell the difference. Okay, so we could give him 2 of each. So he has a 50-50 shot on the first pair and a 50-50 shot on the second pair. So to get it absolutely right, he has a 25% chance of just guessing it correctly if he can't tell the difference. Okay, so it looks like we're onto something here. If we give him enough cups, he's not very likely to actually get lucky. There's a slight problem with this approach is, what if he really can tell and he just makes a mistake? Okay, so it's a model, and he's going to make an error, either human error or he meant to say one and didn't the other. Okay, so what we could do is instead we just get a huge sample size, and we randomize which one he drinks, and then we would stop and say, if we give him that huge sample size, we would assume, well, what if he can't tell the difference between the two, and he's just guessing? What would we expect to see? Well, we'd expect that probably on average, if he's just guessing, he's going to get half right, just by chance, just by luck. Okay? So if he can tell the difference, we would expect that proportion to be much higher than 50%. So this is actually called a z-test. So you can go look that up if you want the actual mathematical formula and how you'd go and execute it. But the point is that we're comparing 2 things. We're comparing the proportion of if he was just guessing to the proportion of what he actually gets right. So statistics also has a logical framework for testing. And they have structure to them, these statistical tests. So these tests typically compare 2 models, and you start with a hypothesis that you assume to be true. Okay, and we call this the null hypothesis. Okay, so in this case, the null hypothesis would be he can't tell the difference. Okay, and so the null hypothesis would say, well, he's going to get about 50% right. So then we look to see if the data supports an alternative hypothesis. Okay, and in this case, he can tell the difference between the 2. Okay, now the thing to realize about this test is with statistics, it doesn't prove anything, and it doesn't tell you which one of these models is right. It just tells you which one is better for the data that you've gathered. And it actually gets a little bit more subtle than that is with the null hypothesis, you never actually accept one of the models, is that you either reject it or you fail to reject it, okay? Because we don't know if there's a different model that would actually be better than both of them. So, okay? So this is just one of the tools we need to apply it at the right time and only under the right circumstances. So an example of this would be A/B testing. Okay, so let's say I have a site and I sell stuff, and at the site I have visitors coming in, and a certain percentage of those visitors become customers. So that's a proportion. We call it the conversion rate of a website or an advertising campaign. So let's say that I come up with a sweet new website, the new hotness. It's just great, and I know it's going to be good, but how do I actually know that it's any better than my old site? Okay. So how would we go about testing that? So the conversion rate's a proportion, and so it's exactly the same as the Diet Coke example. Okay, so we would actually have to, in our advertising, is we need a representative sample. And so we would need to make sure that it's representative, is we would just pick them at random, whether or not they get to go to the new site or if they go to the old site. Okay, and random is because that's the best, it's the best that we can do to get a representative sample. Okay, so then we would send people to the new site, and then we would compare the conversion rates. Okay? So now there are a few caveats of this. I had a friend that they rolled out a new website, and so they did exactly this. They had an ad, and they sent a certain percentage of the traffic over there, and they found out that the new site wasn't doing as good. It was actually doing worse. So they went looking, and they discovered that the new site was broken for IE6, that they were using JavaScript to put something in your shopping cart. And so if you were using IE6, you actually could not purchase anything on the site. So this is really bad, right? So then the question is well, so is that accounting for why it's worse? And so, and you can do that because you can just look at the proportions. So you can just take the proportion of IE6 users and take them out of the sample, and then compare the old site to the new proportion minus the IE6 users, and to see if it was your site, or if it was the design completely, or if it was just that you made that error that you quickly fixed. Okay, so that's z-test, a proportion test. All right, so let's say that we want to sample for a benchmark instead. Okay, so say we have a web application, and the thing we actually want to measure with web application is how many requests can we do per second. So a good tool to use for this is HTTP Perf, that we're going to generate a test load on our web application, and we're going to send requests one right after the other as fast as it possibly can go. So to sample this, so that's kind of the population, so we need to sample out of that. So what HTTP Perf does is that you would pick every 5 seconds. For a given second, you count how many requests you actually got during that second. Okay, so this is an example of all the requests. These are the X's, and then at the start of the red X right here, this was the start of the second, and then we counted how many requests we got during that second. And then the next second, well, we're not sampling it. Okay, so we're actually sending through, in this test, we might send through 10,000 web requests. That'll take about 30 seconds, but we're actually only going to pull out maybe 4 samples from that, out of that population. Okay? So of course, our favorite web application, web server for Ruby applications is Mongrel. So a little bit small up there, but is this Mongrel, and how many do we need to have? I mean, so let's see here.
Run! Jump! Rest! I know we've had a rough day, but I'm sure we can put all that behind us.
So I think, Mongrels is kind of a free-for-all. They're not lined up, they're just going as fast as they can go. So we actually need a pack of Mongrels pulling our dog sled here. Okay, so what we did is we're going to measure the performance of the request per second, and then we're going to make a change. Okay, so we're going to change, like we're going to add caching to our application or something. And we're going to see, well, did it actually, we made that change, is the performance changed at all? Okay, so in this case, it's not a proportion, so we can't use the previous z-test, and so we need a new tool. We need the t-test. We need the t-test. Okay. So the basic premise of a t-test is that, so we have this population and we have these samples. And so the t-test says, okay, I have two samples and they're estimates of the population since we can't measure it directly. And so the t-test will tell us the assumption for a t-test, the null hypothesis, is that these two samples came from the same distribution. So basically this means the assumption is that there is no change. Okay? And so with the t-test, the output of the t-test, the most important part is called a p-value. So p-value is the probability that the effect that we're seeing was just caused by randomness and not by our change. Okay, so the t-test is actually just it's a approximation of the permutation test. The permutation test just looks at all possible combinations in a population and to find out which ones are as bad or worse than the ones that we saw. And they just count up what the probability was that we just grabbed those at random and we ended up with something as bad as we did. Okay? So a quick example here might help. This is R. It's a open source statistics analysis program. It's pretty good. It's pretty hardcore though. Okay, so for instance, say we have the numbers, we can ask R to give us the documentation on, what is the t-test, okay? So one thing, to keep it really simple is, let's say that we sample something and we have the numbers 1 through 10, and we want to see if, the numbers 7 through 20, if those are from the same population. So we can just run a t-test. So this is called a two-sample t-test. So I'm just going to 1 through 10 and then 7 through 20. Okay, that is small. Okay, can we read that better? Okay, so the important parts here is this p-value. We see this is an extremely small number. So that means that if we assume that these two samples came from the same distribution, and then we just randomly pick two samples from it, that we would have, chance in, a couple million, that we would end up with something that bad. So then, in that case, then we say, well, that's not very probable then. So we would reject the null hypothesis that means that they're from the same population. We say, yeah, these are from two different populations. Okay? So before I showed the graph of the average and the standard deviation, and that they can be the same. So let me just recreate that. So I've got A is just going to be, I'm going to sample from a random normal distribution. So you give me 100 samples with a mean of 30 and a standard deviation of 1. Okay, so A is now in that distribution randomly selected from a normal distribution. And let's put B as 100 samples, again with this exact same average. Let's give it quite a bit larger standard deviation, so it's going to vary quite a bit more. Okay, so this is the exact as that graph I had. So if we test these, then we find out that the p-value is is 0.2. So we've got a 1 in 5 chance. See, so these distributions actually overlap quite a bit. So then we would say, well, actually, there isn't a whole lot of evidence that they're from different populations, and they're most likely from the same one. So then we would say that there is no change at all, and they're from the same population. Even if one's a little bit faster than the other, well, it could be just due to randomness. Okay? So the t-test gives us, we got two samples, and we say, are they any different? So like in a performance test, let's say we compare two runs, and on one run I use my Mac, I'm using a Core 2 Duo processor with 3 gigs of RAM, and for my other test, I'm going to use Linux, an AMD processor, and 4 gigs of RAM. Okay? So say I do those two runs, and I run through my t-test. t-test says, yes, there is a difference between these two samples, but then the question is the t-test only tells you that there's a difference. It doesn't tell you what caused the difference. And so this is called confounding variables. So the only thing that you can do to combat confounding variables is basically you only change one thing at a time. You keep everything the same, and then you only change one thing. And then, so that if you isolate it and there's only one thing, then that's the only way that you can have confidence that the thing that you changed is actually the cause of the difference. Okay, so there's been a common trend, I guess. I saw a benchmarking test where, to do it right, you don't want your testing code to infringe on the actual application performance. So you really need two computers, right? You need one computer to be the client, you need another computer to be the server, so that the client isn't stealing the CPU away from the web application. And so one fellow had the idea, is like, well, I don't really have two computers, but Amazon has the elastic computing grid, and they get a virtualized server with these specifications. And that's pretty standardized. So it's been kind of common to do performance testing using Amazon EC2, which is an awful idea. And it's because, it's virtualized. So there's multiple hosts per actual physical box, and you have no control over how many are on there. You just ask for one, and you're assigned randomly, basically, to one of these servers. So you don't know if the benchmark is changed because of the application code, the thing that you're testing, or if it's due to the virtualization environment, or that you just really got unlucky and you're on a really busy host. Okay, so for a benchmark, then there's too many confounding variables. You don't know what is causing a difference, if there is any. But then on the other hand, if you are deploying your application to Amazon EC2, then that's something you have to put up with. So then you would test your application. You would have to have enough samples that you would find an average, so that instead of looking at the performance of the specific application, it's this application on Amazon EC2. That's how you'd have to do that. All right. So in review, we got a few tools now. We got the z-test to test proportions, and we can use that for like A/B testing. We also have the t-test to see if two samples are from the same population or not. So some of the takeaways is, sometimes we change something, we think, that's going to be faster, but my gut tells me. But if you really think something's better, is how do you actually know it's better if you haven't measured it? Okay, so with statistics, it's really easy to make mistakes. That's why it's really important that we have someone double check us, some peer review. There's some really subtle problems that we may overlook. Even statisticians, when they're working on things, they always collaborate with other statisticians because it's so easy to make mistakes. And so a good way of doing that is to automate your test harness that's actually driving your test so that it's always the same. And one of the nice byproducts of that is that then it makes your test easily replicated by someone else, so then they can peer review it. So I'm sure we all know of a really handy, cool language we can script tests with, and to automate our graphing as well. So when we come back, so some resources is the R project. Again, it's open source, runs on multiple platforms. It's great for statistical analysis. These guys are hardcore. They got great documentation. A lot of the documentation is assumed that you understand all the statistic principles, but as soon as you get some of the lingo down, then you can kind of figure it out, and Wikipedia's your friend. Okay, another excellent resource is on Peep Code. They have an episode on benchmarking with HTTP Perf, and it is actually quite excellent, where he actually goes through a Rails application and he tests the performance of it, and then he compares that with purely dynamic, with page caching, and then with action caching. So he's not specifically using a t-test in that Peep Code. He actually just looks at standard deviations, which is actually the exact same thing as a t-test. He just doesn't run the function. He just does it with an intuitive proof. But it's quite excellent, especially his description of how you would sample an application. And of course, Zed Shah. Probably familiar with his rant on programmers need to learn statistics or he'll kill them. It's a good rant for identifying some of the common misconceptions that we have, at times, the compounding variables. We should never measure how many users can this system handle, because how do you measure that? What is a user? It doesn't make any sense. You actually need to go straight for performance, so like requests per second, and don't bother with users. That's a meaningless metric. Also, fantastic resources. His write-up when he was doing some Ruby, Odium, and Lucene for text searching. And that is actually a fantastic write-up that he did, in that he actually steps through the entire process of how he bootstrapped the analysis, how he sampled the test to find out how many samples he actually needed to run. He has on there all of the data and the testing harnesses and all of his analysis scripts with explanations of why he did everything. It's a fantastic write-up. Also, kind of key here to statistics is just dealing with the data itself and to find meaning from a graphical representation. So, of course, Edward Tufte is fantastic for that. I highly recommend the visual display of quantitative information, how you can convey information through quantitative information through graphs and such. Alrighty, any questiones? Hope not. So.
What do you need in terms of sample size to be like a representative sample? Like you sample 2 seconds over the course of is that enough?
Okay, so the question was, how many samples do you need to know that you're representative?
What makes a representative sample?
Well, representative sample is, what I mean by that is you can't, you can't take a sample of convenience, right? So if I'm going to find out what's the average height of people in the world, then a non-representative sample would be just what's convenient, like people in my immediate vicinity. Okay, so the best way so it's really hard to manufacture a representative sample, especially if you're not sure what you're measuring. So the best you can do is to randomize it. And so if you randomly select out of that population, then on average, if you you do several of those samples, then those samples will be representative.
You have a run of, say, several minutes. You pick 2 seconds. Is that enough? I mean, 1 second probably is enough. Is 2 enough? 3?
It depends on what you're measuring. So usually, like if you're doing a run for performance, then you would you're going to take a sample, and out of that sample, you're going to calculate an average for that sample, and then you're going to look at sample averages. So there's the central limit theorem, which means that the things that we're going to measure aren't normally distributed, but the normal distribution is really easy to work with. But it turns out if you're looking at, there's the raw data of the sample, and if you look at a mean, or it's called a statistic. So a parameter is a population, like the average weight of an elephant, that's a population. And so the average is called a parameter. And out of that sample, if we take an average of the sample, that's called a statistic. So any statistic that you are taking the average of, that if you have enough samples that those averages will end up being a normal distribution regardless of what the original distribution was. And that magic number is about 30. So if you get about 30 samples and you're looking at the mean, then you're good to go.
So are you saying that if you take 2 samples such that the average of each sample is the same, you've got a good representative sample?
No.
It's like the population of Utah, how many are men and how many are women. If you take this room, you're not going to get a very good sample, but if you make it more convenient for us.
That's right. Okay, so your question again was, can you ask it again? I'm sorry.
Sure. The question was, if you take 2 random samples and you're not sure what size would constitute a good random sample, if the average of each of those 2 samples is it's close to each other, does that indicate that you've got a good random sample?
Not necessarily, because they could completely have a chance. So there's a whole branch of statistics called the power test. So the power test is, say, I want to be able to make a decision at the end of this with like a 95% confidence that I'm right. And so then you would say, okay, what's my population? What are the basic estimates of those parameters? And it tells you how many samples you would actually need to have.
Can you address the difference between a random sample distribution and a uniform distribution, for example?
What do you mean?
Random there's some relationship between randomness of data and uniformness of distribution of that random data. if you're randomly selecting samples out of the population, you may not be getting a uniform representative sample set.
That's true.
Is there anything you can do to clean your data to make sure that the statistical population is represented by your...
Well, you definitely have to make sure that you have good, clean data to start out with. Now, I guess I was a little bit confused because uniform distribution is actually something very specific, and it doesn't follow a bell curve. It's just a straight line is uniform distribution. But I think your question is, say I have a population and I grab randomly out of it, I could randomly pick a really bad section of it. Is that right? Yeah. So the way to mitigate that is that the random selection for the sample is that it's not a one-time deal. So you say if we select randomly that on average, if we keep repeating the test, that on average it'll even out. So one time we could get a really good one time we get a really bad one, and on the average we're going to get a fairly representative sample. So it's not just a one-time shot. That's why you have to have multiple samples from a population. Does that answer your question?
Well, it begins to. It seems like when you're testing software, there's all sorts of crazy artifacts that can deal with latency versus certain maybe a periodic behavior, and it could just be that the randomness of your sampling happens to fall if the speed with which you can sample data completely misses these blips that always fall between the spaces where you're doing that. So are there techniques for discovery that you have this crazy outliers like that? Like you said, the IV6 thing. Yeah. We're just not getting any data from that. Or is that just more of an art than science at that point?
It is an art, really. So, I mean, the only thing that you can do is that those artifacts and if you randomly sample, is that eventually, if you have enough samples, that you're going to see some of that funky behavior. So, it's possible that you're never going to see it if you're randomly sampling, but that's really unlikely. This has a really low probability for that.
The size of your error bars, you said, okay, we know that there's this many data points in this population, but we've only sampled X% of them. So that means our error bars are a certain size.
That's right. Exactly.
You got to look at that.
Yeah. More samples gets more refined, but then you have to take it. That's a tool for discovering those, but then that might be able to discover the outliers, but the statistics isn't going to tell you whether those outliers were just by chance or if it's actually a problem with the system. And so that's why it turns over to, you have to understand the underlying causes of the system. And statistics it's actually a really, it's not a very insightful tool. It's a powerful tool in the right context, but it's not this all-knowing thing. Really, you use it as a tool for your specific domain knowledge.
With Bayesian statistics, you can find stuff like causality. Has anyone ever tried to aim that at Perf or anything like that?
Okay, so the question was, with Bayesian methods and statistics, then it's a way of defining causation, and if anyone has used that in HTTP Perf. Small nitpick, Bayesian statistics cannot prove causation. Okay, so what a Bayesian does is it uses a probability model. It's an inverse probability. So it's basically like I deal you from a deck of cards, I deal you 5 cards, and depending on the 5 cards I got, then I can estimate the prior probability whether or not the deck was shuffled or not. Okay, so it's an inverse probability, it's a reverse one. So Bayesian methods are very cool. I don't know if they've been applied to HTTP Perf or not. That's actually something to ask Zed about, because when I ran into Zed, I was taking my stats course, and I was like, and I asked him a question, and he was explaining some nuances of the t-test, and then he's like, "Have you looked at Bayesian statistics?" And I had used Bayesian statistics for like machine learning classifiers, but I didn't know that you could actually use it as a general purpose statistical tool, and I just actually found out about that last week of how you actually use it. So, sorry, but it sounds interesting. Sounds really cool.
So I'm wondering, with Perf specifically, why would you use a sampling method when you've actually measured the entire population?
I'm just trying to wait.
You can measure the entire population. I don't know. I'm not a statistician. So the question is with HTTP, why do you even sample if you can look at the full population? So I know that sometimes you can do the full population, but you have to realize that too when you're doing a performance benchmark, is that you're looking at a specific time interval, so that's not the actual population anyway. It's just that segment of a population for a given time interval, which is a sample, right? Because you can't actually measure, the performance of all time. The other thing that I know about is part of it is just with the sampling. Then part of it is computation. Not that that's really that awful. I'm sorry. I need to ask Ed on that one. I'm not. I don't have a good answer for you. I'm sorry. So, you have an answer? I'd like it.
Basically, a lot of times when you're doing statistics, you're making decisions on things that don't exist yet. So, like your website's not in production, and you just want to see, which web server should we use, or what OS should we use, or how much RAM, or whatever. So you basically set up a bunch of scenarios, and every scenario you run the tests on, and they're not real production data. You don't have coming from 10,000 different IP addresses. So you're basically just using statistics to figure out what probably is the best way to go. So it's not your data set's not even real anyway, in the sense that it's real production data. So it's just a theoretical world that you set up temporarily in different scenarios.
And I know with the sampling too is that if you look at the full population, then you have one distribution. Where if you have samples, then each one of those samples is its own distribution. And so that gives you a lot more powerful tools to analyze it. But that was a great answer. I wish I would have come up with it. Okay. Thank you much.